Hello and welcome to this guide to make your own emulator. The chosen emulator for this series will be Chip 8. Why Chip 8? It's a very simplistic 8-bit microcomputer from the mid-1970s. It is a simplistic computer, so it will not be all that hard to emulate the the Chip 8 microcomputer, and it's a nice step up to create something more useful or something like a Game Boy Advance emulator or like a Super Nintendo or whatsoever. It will also give you a good uh, well view of how computers work and how assembly is working, and it will be a great way and a fun way to learn programming. So before we get started, I do require you to know at least a little bit about programming. I will explain a lot over the coming videos, and I will help you a lot when I do expect you to know how do I declare an integer, what is an array, what are switch statements, simple conditions, um, just the basics. I will explain a lot of in-depth information which will be useful in other projects and later on in the course, but it I won't explain you the very basics of programming. So before we even begin programming anything, I will require you to read a 100-line page which I wrote down about binary and hexadecimal. We will be using calculations with binary and hexadecimal a lot, so you will have to understand it before you will understand the code we are about to write. So I will add a pause in the video, and after that we'll start writing the base of the Chip 8 emulator. So now you've done that, I will open up a little wiki page and we'll show that to you. So this is a page about Chip 8. It has a lot of information. It's really simplistic, and we will be using this as a reference a lot. I will also use this page in smaller sections, but it's much more complicated and much more how a documentation would look like. So to start off, we will start reading this bit about the basic information of the Chip 8. I already know most of this because I already read it. We will be using Java for this emulator, and I will stick to Java a lot, but there is a little problem with Java. We don't have unsigned or types except one 16-bit character type. The fact that Java can remember negatives is because they use signed types. They will be using one of the bits in a binary representation. It's called a bit. They will use one of the bit to determine if it's a negative or a positive value. So that will effectively reduce the amount of space we got available, and it is affecting some of the shifts, binary shifts and calculations we are doing with it. So we will be using the chart type to represent almost anything in the entire chip emulation. So I will be using Eclipse, Eclipse Juno. Why Eclipse? I like Eclipse. You may not like it. I don't care. Use a different program. It's Java. It's not the IDE which is sticking you to use it. So I will create a new project called Chip 8. I will be using Java 1.7, or as more known, just Java 7. We'll create, I will create a couple of packages for the emulator. and for the chip itself. The emulator will contain the frame, and the chip will be the actual chip itself. So in the package chip, I will add a class called chip. Before I even start coding anything, we will have to know a bit about the chip 8. So I will read the memory values and stuff like that. So a chip 8 has 4 kilobytes of memory, which is 8-bit memory. We'll be using a char array to represent the memory. Don't worry about commentation. I will upload these files to GitHub, and I will add comments or commentation on the classes and functions and variables once this video is ended, because it will take way too long if I do this all right now. Alright, let's continue. I will add a function init which will initialize everything for us so we can reset the emulator. So now you might be wondering, why did I add the array of 4096 bytes or spots? Well, a kilobyte is not this kilobyte, which is 1000, but it's this kilobyte, which is 8024. So I multiplied it before and you will get 4096. But the actual chip 8 has to do everything within that given memory. We will be abusing stuff around, or abusing Java and emulating to create more memory than it actually has. So now when you know that, we'll step on to the next heading, which is registers. Chip 8 has 16 registers called V, and in documentation it's also used as V, so we will stick to that. It has 16 registers, and the last one is used to indicate carry, borrow, and collision. We also have an address pointer called I, which is 16-bit wide, but only 12 bits will be effectively utilized. Alright, these registries are basically like an assembly. You can store a value in it, and you can reference to that value in the operation codes later on. Alright, so we will continue to this stack, which is an address pointer array. So we will create again the char with a stack, and we will create a stack pointer. We will initialize the stack as a char array of 16, as it can use 16 levels of nesting. So it can call 16 subroutines, and if then another subroutine is called, it will crash. It can't know. We don't got any more space in it, and you will probably overwrite other stuff. For addresses we use this format, but that doesn't matter right now. So we also contain two delay counters, which is not documented how many bits they are, so we will just use a basic integer for the delay timer and the sound timer. They will tick down at 60 Hertz, which equals each second will have 60 updates. Alright, well, the next heading is input. The input is a hexadecimal keyboard, which means we have 16 keys. With all those keys, which will be stored in a char array for now. It could be an integer array, as we can define it how it's implemented ourselves. So I will actually do it a byte array. Alright, so the input is hexadecimal, so we have 16 key states. So the keys will be a new byte array with 16 spots. There is no way how there is defined how we will input those values, or how it should be documented, as there are two operation codes which will allow us to make that specific check, so we can do whatever we want and whatever we like to decide. Alright, and there's only one step to do before we can create some actual coding, which is the display, which is also undefined how to define the actual grid behind it, but we will use 0 for black, 1 for white, as it's more easily to use it in the collision detection, which is documented. So we will, as it is stated, the display resolutions is 64 by 32. So we multiply 64 by 32, and that will be our dimension. There is also a sound beeping when the sound timer hits 0. Wait, no. As that beeping sound displayed when the value of the sound timer is non-zero. So it will constantly bleep before or until it equals 0. We'll don't have to store any value on that, because the sound timer is more than enough for that. So, well, that will be basically our entire class about chip data. We will start with writing a core run method for the chip. So we will create a new function called, well, I will call it run. In this function we need to do several things. The first one is to fetch an operation code, referred as opcode. Then we need to decode the opcode, and during the decoding we will also execute the opcode. So this sounds like it's all complicated with opcodes and shit and all that crazy stuff, but it's not. The Wikipedia page just defines how each and every operation is defined, and we only need to implement that in the system. And I will help a lot on how you will create those. So in the first part we will cover the fetch and the first step on decoding, and then I will end the video. So to fetch an opcode we have, oh wait, I forgot a memory pointer. There is one additional memory pointer, which is called program counter. The program counter is the initial point where each and every program will start. The program is loaded in at position of hexadecimal 200, which I have no idea how large it is. So to do that you can use view programmer, and then you will get this fancy view, and I will write in 200, convert it to decimal, and 512. So at index 512, or at slot 512, or each program will start. That's really important. So to fetch the operation code we will define a new char, and the char will be, I will call it opcode because it's an opcode. The opcode consists of a 16-bit value, but as our memory is only 8-bit, we will have to merge 2 memory slots into one opcode. So we will need to add memory at position of program counter and the position at memory program counter +1. To do this, we will add some bitwise ending. We will use bitwise OR, not AND, OR. It will check if where is it? Or shift or there. There we go. It will check if either of the two values has the bit set to true. If it does, it will add it to the new value. So basically what we got now is the program will check 2 bytes, merge it together into one single byte. But that's not what we want. We want one of the two to be shifted to represent a new value. So we shift the first one to left 8 positions. So we shift this bit an entire byte next, or an entire byte to the left. So if, for example, the memory pointer pointed at 000001, this one would be now about here, those 8 digits. So now Java says, hey, I'm not sure if I can contain my integer in this character. We are sure our character or this value will be an integer, so we cast it into a memory or into a jar. This is how you fetch an operation code, and I will show a quick demonstration of it. Yeah, integer string to hex string. This will convert our opcode into a hexadecimal representation, which is easier to read for this case. I will add a quick main class so we can run the chip quickly. Public static void main string with args. We will create a chip, C, which is a new chip. We will initialize the chip and we will run the chip. So there we go. Our opcode is 0, which is highly correct because we don't get anything in our memory. So to decode a operation code, we will use a big switch statement and a default statement, which will cast the system exit 0 and report to us that this opcode is unsupported. So this will add a little won't break the line, and so this will become or will come at the same line as the operation indication. So we know like 0 unsupported code. So if we take a look at the operation list, code list. Oh fuck. Damn it. There we go. We can see the operation codes start all at the first one, at the first nibble of data, which is the first 4 bytes. If the first nibble is defined multiple times, the last nibble or last byte will contain extra data about what to do. And this one is the first nibble, and the last nibble, which will declare this is what we will do. And for example, at 8, it's also the last nibble. At F, it's the last byte, which will define what we will do. So now we know that we can use an ANDing operation, bitwise ANDing, which will check both bytes, or in this case bytes, if it has one on this or both bits flicked. If so, it will reset that bit to true in the resulting value. So to do this in our code, we will use, or in our switch statement, we will end the opcode with 0xFOOO. So this will mean we will grab all values from the first nibble from the opcode. So if, for example, if it is D draw at xi with height 4, it will return this. So we can split each opcode into its operation, and this will allow us to process each code. So, but as you've seen on the list, it's actually not that simple, because it defines multiple operations for some of the keys. For some of the keys, operation codes. So I will do the example on 8. If our case equals 8,000, which is or 8 series, we notice, hey, our last bit, or last 4 bits, last nibble, is also giving us data. So I will add comments about this. Contains more data in last nibble. So in this switch statement, we will add another switch statement, or in this case we will add another switch statement checking the last nibble, which we will do it the same way. We use bitwise ANDing on the last nibble instead of the first. So here we use the first, here the last. So if our case now, which will result in, for example, OX001, it means that our operation is set Vx to Vx bitwise or Vi. It sounds all gibberish right now, but I will explain it once we will start actually coding. So if our case now is 000, it is the operation code is 8xy0, which is, oh, why I keep opening the wrong file? Which is this. For good measurement, we will add this to every code we implement. I will also add a default case to this one and say the same thing: system error, print line, unsupported, opcode, system exit. So this is including the first part, but I will give you an assignment. We have our display, but we can't see it. As you can see here, only this is visible, and we don't like that. We really don't like that. So we want a Java frame. Can be used anything you want to use. If you want to use DirectX, heck, do it. I don't give a crap. Just make something which displays the display array onto the screen. And don't use these dimensions. They are small, really small. Use something like 10 times scaled up, so you will get 640 times to 320, which is much more bearable. It's not all that hard to do. You can keep it simple or you can make it as complex as you want. But I will post the solution to this on Sunday. Yeah, I will post the solution or a solution to the assignment on Sunday, and I will cover my solution and some reasons why I did that. Well, that basically concludes it for the guide. I will see you guys in the next video.